Here I've got a nice problem from the Canadian National Math Olympiad from the year 1995. So longtime viewers of the channel might know that I'm a big fan of Canada. In fact, my wife and thus my kids are dual citizens with Canada and the United States. Her family lives in Montreal. So anyway, let's get into this problem. So we want to consider the following function, which I'll call f, and we have f of x is equal to 9x over 9x plus 3, and then our goal is to find the sum as n goes from 1 to 995 of f of n over 1996. So let's see what the problem is. So we'll set f of x equal to 9x over 9x plus 3, and then evaluate this sum into a nice closed form. And here we have the sum as n goes from 1 to 1995 of f of n over 1996. So notice 1995 depends on the year. Okay, so in order to get an idea of what's going on here, we're going to play with a smaller example. So let's look at the sum as n goes from 1 to 5 of f of n over 6. So the important thing here is we're going from 1 to an odd number of n over the even number that is right after that odd number. I guess we could do one smaller example than this, but I think this is sufficient. Okay, so let's see what we have here. This is going to be f of 1 over 6 plus f of 2 over 6, which is 1 over 3. Plus f of 3 over 6, which is 1 over 2, plus f of 4 over 6, which is 2 over 3, and then plus f of 5 over 6. Now, one thing that immediately jumps out at me is that these two numbers right here, 1/3 and 2/3, add up to the number 1. And then similarly, this number right here, 1/6, and then this number right here, 5/6, also adds up to 1. So maybe there's something going on there. So let's maybe group those together just to see if this works out nicely. So we've got f of 1/6 plus f of 5/6. So like I said, we'll group those together. And then plus f of 1/3 plus f of 2/3, and then plus f of 1/2. And now let's stick these into the function and see what happens. So this is going to be, let's see, 9 to the 1/6 over 9 to the 1/6 plus 3 plus 9 to the 5/6 over 9 to the 5/6 plus 3. And then here we'll have 9 to the 3rd over 9 to the 3rd plus 3 plus 9 to the 2/3 over 9 to the 2/3 plus 3, like that. And then finally, right here, we'll have 9 to the 1/2, which is 3, over 9 to the 1/2 plus 3, which is 3 plus 3, which is 6. Now let's see if we can maybe simplify these at all. Well, I think even though it seems kind of painful, our best bet is to find a common denominator, which will be just the product of these two things. So let's see what we get if we combine these via a common denominator. We'll have 9 to the 5/6 plus 3 times 9 to the 1/6, and then plus 9 to the 5/6 times 9 to the 1/6 plus 3, and then this is all over 9 to the 1/6 plus 3, and then 9 to the 5/6 plus 3. So let's just say we're working on these two terms right now. And then if we need to, we'll do a calculation on those other two terms as well, but maybe we'll see some structure just based off of this. Okay, so let's see what we get. 9 to the 6th times 9 to the 5/6 is 9 to the 6/6, which is just 9. And then we get another copy of 9 right here because this is 9 to the 1 as well. So that adds up to 18. So just to reiterate, that's what we get from this times this, and then this times this. And then we'll have 3, but notice that 3 is 9 squared. And then we'll have 3 times 9 to the 1/6 plus 3 times 9 to the 5/6. So I'll write that as 3 times 9 to the 1/6 plus 9 to the 5/6. And this is all happening over this. But let's see what we get if we multiply this out. So again, we'll have 9 to the 1/6 times 9 to the 5/6. That'll be 9. And then we'll have 3 times 3, that's another 9. That adds up to 18. And then we'll have 3 times 9 to the 1/6, 3 times 9 to the 5/6. So this is going to be 3 times 9 to the 1/6 plus 9 to the 5/6. So notice the numerator is the same as the denominator, so this adds up to 1. So what we have here is this guy is just the number 1. And then I bet you can see similarly, this guy right here will be the number 1 as well. And then this right here is obviously 1/2. So our answer is 2.5. So I'll just write that as 2 plus 1/2, or 5/2. So the important thing here is that when we combined f evaluated at something plus f evaluated at 1 minus something, we got the number 1. And so let's maybe prove that lemma in general, and then we'll jump into the main solution. So on the last board, we gained some data for the truth of the following lemma. And that is, for all x bigger than 0, f of x plus f of 1 minus x was equal to 1. And so let's prove that in general. So let's just start with our f of x plus f of 1 minus x. Then we'll expand that in terms of our function. So this is going to be 9 to the x over 9 to the x plus 3 plus 9 to the 1 minus x over 9 to the 1 minus x plus 3. And so the fact that we've got a 9 here and here and a 3 here really begs us to divide a 3 out of the numerator and the denominator of each of those. So let's see what that leaves us with. So in the numerator, we'll have 3 times 3 to the 2x minus 1. Here we're obviously using that 9 to the x is the same thing as 3 to the 2x. And then in the denominator, we'll have 3 times 3 to the 2x minus 1 plus 1. Okay, good. Now let's do the same thing over here. So if we factor a 3 out now, we'll be left with 3 times 3 to the 1 minus 2x over 3, and then 3 to the 1 minus 2x plus 1. So something like that. So this is a little bit trickier to see, but that's what happens if you replace this 9 to the 1 minus x with 3 to the 2 minus 2x. So let's maybe write that down. So 9 to the 1 minus x is 3 to the 2 minus 2x. For the same kind of reason as the one right above it. Okay, but now that we've got this set up, we can cancel some 3's in the numerator and the denominator. We'll cancel that 3 with that 3. Then we'll cancel this 3 with this 3. And then we'll multiply this second term by 3 to the 2x minus 1 in the numerator and the denominator. So let's see what that leaves us with. So this first one just comes down. We have 3 to the 2x minus 1 over 3 to the 2x minus 1 plus 1. And now we'll have 1, because we're multiplying by the reciprocal of 3 to the 1 minus 2x, over 3 to the 2x minus 1 plus 1, where I've distributed that through and then changed the order of our summation. But now let's notice I add these together and I have the same thing in the numerator and the denominator, so that leaves me with 1. But that's exactly what we needed to show for this lemma. Okay, so let's get rid of this proof and we'll apply this lemma to our final goal. Now we're ready to finish this off. And before we do that, I'd like to point out that I played around in Mathematica to try to get a guess for the value of this sum. And Mathematica will not simplify the output of this without a lot of work. So that's pretty interesting because it doesn't see that trick, which is this lemma that we've just proven. Okay, so anyway, let's get into it now. We've got the sum as n goes from 1 to 1995 of f of n over 1996. So I'm going to write this as the sum as x goes from the set 1 over 1996 all the way up to 1 over 1995 over 1996 of f of x. Just to put it more in terms of what we have up there. And now I'll break this set into 3 disjoint parts. One part which is just equal to the number half. Notice the number half lives here, right in the middle, where we have 998 over 1996. That's equal to a half. And then everything below a half and everything above a half. So this is going to be the same thing as the sum as x goes from the set 1 over 1996 up to 997 over 1996. So that will be our first part, f of x. And then plus the 1/2 term, but I can just rewrite that as f of 1/2. And then plus the sum as x goes from 999 over 1996 all the way up to 1995 over 1996 of f of x. Great. But now I'll perform a change of index for this last sum. And this change of index will replace x with 1 minus x. But now notice if we replace x with 1 minus x, that's going to fold this set right here into this set right here. And so we'll be summing over the same set. So that'll give us the following setup. We'll have the sum as x is in the set 1 over 1996 all the way up to 997 over 1996 of f of x plus f of 1 minus x plus f of half. Okay, but f of half is the same thing as it was when we did our example. That was equal to 1/2. And then furthermore, our lemma said that this was equal to 1. And so how many 1s are we adding together? Well, notice there are 997 terms from this set. So there are 997 1s. So this gives us 997 plus 1/2 as our final value for this sum. And that's a good place to stop.